Hello, everyone. Good evening, Shivanand. Yes, so we are back with another class, and today we are going to continue a little bit of hashing, and we are going to see hashing on strings. But before we begin, let us congratulate the winner of the previous assignment. So the last assignment on hashing, the best submissions, the fastest submissions, were by it's your boy Rishi Sharma. So that's their username. So congratulations, Rishi. Someone from the team will be contacting you, and they will get your address to send out some cool goodies your way. All right. Now, if you also want to participate in the assignments, then there will be a link in the video description down below. Over there, what you can do is you can find some assignments that help you practice whatever you have learned in the class today, so that you can apply things and internalize them. All right. So today, once again, we are going to cover hashing, but we are looking at hashing specifically for strings. And there's one more thing that we are going to cover today, which is the Rabin karp algorithm, which is one way of hashing over a particular string. Right? This is for substring matching. All right. Perfect. So let us begin. Let us start directly with a very simple question. The question goes something like this: that you have been given a string, let us say S. All right. Now you have to find whether it is possible to somehow permute or somehow rearrange the letters of the string B, somehow to permute or rearrange the letters of this given string so that it can be represented as a concatenations, a different, so that it can be represented as 8 different concatenations of some substring, of some string, basically. Right. So let us take an example, perhaps. Suppose that I have the string AABB, right? So currently, if I look at this string, is this particular string a concatenation? So let us suppose that A equals to 2. Can I somehow break this string down into 2 parts such that both these parts are equal after rearranging the string? Yes, I can. Right. So if I currently this is not currently this cannot be these partitions are not equal. But what I can do is I can perhaps rearrange it like this: A B A B. Right. This string is just a permutation of this previous string. And now if I see in this string, yes, there are 2 occurrences of the exact same string. Is that clear? So basically, you will be given a string like this, and you will be given a number such as 2, and you have to tell me if it is possible to rearrange this original string such that it becomes a concatenation of A similar strings. I hope the question is clear. Right? So what approach can we come up for this particular question? Let us always begin whenever we solve a problem. We always try to begin with the absolute brute force approach, because as we know, being able to solve a problem is always the first step. Right? Let us forget about the optimizations. Let us do the optimizations later. Let us first solve the problem. So what will the entire brute force look like? Well, we know that we have a string, let us suppose S, and let us suppose the length of string S is N. So we can try all permutations. We can try all permutations. So let us suppose that we have some permutation of the string S. We have some permutation of the string S, and we have the value of A. We have the value of A. Let us suppose A is 4. So we can check, we can split this string into 4 parts, and we can check whether this is equal to this, is equal to this, is equal to this. Simple enough? Yes? That will be the brute force approach. What will be the time complexity of this approach? Well, first of all, how many permutations, how many solutions do we have to check through? How many solutions do we have to check through? How many permutations can be there in the worst case? If the length of the string is n, if the length of the string is n, then the number of permutations will be n factorial. All right, and given a particular permutation, we'll also have to check whether it satisfies this property. So that will take an extra order of n time per permutation. So the total time complexity will be order of n factorial times n, which is pretty bad, but at least we solved the question. Right. Now, as most of you have already started pointing out, so Ashita is asking to repeat the question. So let me quickly repeat the question once again. So the question goes something like this, that we have been given a string S. Right? We have been given a string S, and we have been also given a number A. Right? Now we have to check whether it is possible to permute or rearrange this original string such that it can be represented as a different concatenations of the same string. Right? For example, if I have this string AABB, then currently I cannot represent this as two different concatenations of the same string. Right? Suppose that A has been given as 2. However, if I rearrange this string into ABAB, now I can say that, okay, because A is 2, I can represent this string as two different concatenations of the same string AB. Right? That is the question. And the brute force approach that we saw, that simply involved trying all the different permutations and checking each permutation separately, which was pretty slow, but at least it will give us the right answer. Right? This is the brute force. All right. Now let us talk about the optimized approach. And yes, so both Vaishnav and Parth have given the right approach over here. So has Akshat. Akshat has also given the right approach. Animesh, your approach is not quite correct. Right? So what the correct approach over here is, the correct, Prakash, let us be sensible over here. Prakash, these kind of comments are not acceptable. Okay. Moving on. So what we can do over here is, we know that this string S, suppose that this string S can be represented. Suppose for now that it can be permuted and represented as a concatenations of the same string. Right? Then what can we understand from that? What can we understand from that? Let us suppose we break this down into 8 different parts. Suppose we break this down into 8 different parts. After the permutation, we know that this particular substring has to be the same as this particular substring after the permutation, right? And so on, this also has to be the same as this, and this also has to be the same as this. So what do we know? Suppose a character comes over here, right? Suppose this character is A. So we know that this character must also be over here, must also be over here, and must also be over here. Right? Similarly, if there's a character B over here, this is how the permuted string should look like. Right? Suppose there's a A over here and X over here. So this is what the permuted string should look like. Yes or no? All right. So what can we basically say from this? We can see that whatever character comes, right, for any character, right, the frequency of that character or the number of times that character occurs in the original string, that has to be a multiple of A. Right? It has to be a multiple of A. Why so? Because if it is not a multiple of A, then you will not be able to make A different copies of it. You have to make A different copies of that same character to repeat that string. So it has to be a multiple of A. The frequency has to be a multiple of A. All right. So this is very simple now, right? This is very simple. All we have to do is, we have to go through the string, and maintain a count of each character. Right? Count each character. Right? And then check for each character, check if the frequency is a multiple of A. All right? Is that clear? Perfect. All right. So this we have to understand over here that this must go both ways, right? This implication must go both ways. So we have so far established that if S has the property, then every character occurs some constant times A times. Right? That is what we have established. But that is not sufficient, right? That is not sufficient. We have to establish that the other way is also possible. That if you have any such string, then you can always rearrange the string into a different subparts that match, right? And that is actually pretty simple to see. That is actually pretty simple to see. What we can do is once we have, let us suppose that we have several characters C1, C2, C3, C4, right? And all these characters occur in some constant, let us say alpha times A, right? This occurs beta times A, this occurs gamma times A, this occurs delta times A. Right? Now what we can simply do is we can start putting these characters in, right? So we can put C1 alpha times. So this will be alpha times. Then we can put C2 beta times. Then we can put C3 gamma times, followed by C4 delta times. Right? So this particular thing will give us one part of the string, and then we can simply repeat this A times. We can simply repeat this A times, and that will give us these frequencies that we so desire. Right? So we see that yes, this implication goes both ways. So this is both necessary and sufficient to solve our problem. Right? So the solution now becomes very simple. Just go to the string, count each character, and at the end we just have to check for every character if its frequency is a multiple of E. Yes. Perfect. Let us see some other approaches that we have. Sai is saying we first check if length of string is multiple of A or not. If it is, then we go with the solution, else returns false right away. Yes. So Sai has a very nice optimization over here. Sai says that, hey, if the original string S, let us say the length of S is suppose 10, and let us suppose that A has been given to you as suppose 4. Now we know that no matter what you do, no matter how you commute or what substring you choose, if you have a string of length n, you cannot make 4 substrings out of it of the same length. Right? You cannot make 4 substrings out of it of the same length. Why? Because simply 10 is not divisible by 4. Right? 10 mod 4 is not 0. Right? So this is one check that we can very well do. At the start itself, we can check if the length of the string is a multiple of the value A. Only then should we continue with the rest of the solution. Otherwise, we can very quickly return false. That's a nice optimization. Thank you, Sai. All right. Perfect. So I hope that you guys will be able to code it. Yes. So how do you count the frequency? How do you count the frequency of a particular character? Well, this is easy if I know what the underlying character set is. If I know that my string consists of only lowercase a to lowercase z, then it is simple, right? I just have a frequency array of size 26, right? One for each character. But what if I do not know? What if I do not know what the underlying character set is? Then I can use something like a hash map. And that hash map will take care of figuring out the underlying character set for me. It doesn't really matter what characters I see. Perfect. All right. So what will be the time complexity of this optimized approach? Let us suppose that we are using a hash map, and let us suppose that the amortized time complexity of checking or insert in a hash map is order of 1 amortized, right? Or basically, let's not say amortized, let's say expected, right? So what will be the overall time complexity? Well, now we are just iterating through the string and counting the characters, right? And finally checking if each of the values is a multiple of A or not. So this is very simple, order of n plus, so n is the length of substring plus order of delta, right? Delta is the size of character set. And we always know that size of character set has to be less than or equal to n, right? Because in the worst case, every character can be different. So I can just rewrite this as order of n. So that is the time complexity of the optimized approach. Is that clear? Perfect. So what we see from here is that all these things are variants of hashing. Right? Calculating a hash. So over here, our hash function was slightly different. Our hash function over here was just the frequency count of characters, right? And whenever we are solving problem related to hashing, we might have to choose our own hash function to make sure that it aligns with the problem that we are solving. All right, perfect. So let us look at one more question perhaps. So suppose that we have been given an array. We have been given an array A of size n, and this array consists of n strings. All right. Just a second. Sorry for that. So we have been given an array of n, and this array consists of n strings. We have to return the groups of all strings, which are anagrams, Right? This is a very simple question again. So let us quickly understand the question. Suppose that I have an array that looks something like this. Right? So array is cat, dog, god, right? Act, and fan. Suppose that this is my particular array. So over here in this array, if I rearrange the values, I can see that cat and act, they are anagrams. Right? So first of all, does everyone understand what an anagram is? What an anagram is? So two words are anagrams. A and B are anagrams. If and only if A can be rearranged to look like B. Right? For example, the words dog and the word God, they are both anagrams because there is one G, there's one O, there's one T. I can rearrange them to look the same. Right? Now the question is that we have been given an array and we have to return the groups of all anagrams. Okay, so over here, if this was given as the input, then our output will be what? Our output will be. So let us quickly number all these values. So suppose this is 1, this is 2, this is 3, this is 4, right? This is 5. So our output should be a list of lists. Right? Our output should be a list of lists. The first group is 1, 4. Right? 1 and 4, they are anagrams. The second group can be 2, 3 because they are anagrams as well. And in the last group, I have 5 separate because fan is not an anagram with any of the rest of the strings. All right. So given this as input, we have to give this as the output. Is the question clear? Is the question clear? Perfect. So let us once again look at the brute force solution. Brute force solution. Right. In the brute force solution, what we can do is we can start with the first string. We can start with the first string, basically the A of 0, and we can compare it with the rest of the strings. A of 1, A of 2, A of 3, A of 4, A of 5, and so on. Right? We can check each string with each of the other strings. While checking this string, we have to check for anagram. Check for anagram. How do we really check for anagram? Should we try all the possible permutations? Should we try all the possible permutations to check for an anagram? Not really, right? Is there any better way? So given two strings, we have to check if they are anagrams or not. Is there any good way of checking if two strings are anagrams or not? Yes. So suppose that we have been given a string A and a string B, and I have to check if A and B are anagrams. I mean, the brute force approach will be to check all permutations and compare. Right? That is very, very bad. So what we can do is we can otherwise check the frequency of each character. Right? The frequencies have to match. And once again, if the frequencies match, then they are guaranteed to be anagrams. Right? Cool. We have another approach over here. So Ankush is saying that what we can do is we can simply add. The ASCII values. Now this might not always give us the right answer. For example, suppose that we have the following strings. So we have A and D, and we have B and C. Right? So we know that the ASCII values of these is 65 and 69, and this is 66 and 67. Okay, so this is 68. Right? These are the ASCII values of these. And if we see, then yes, 65 plus 68, this is actually equal to 66 plus 67. Right? So if we were to compare these two strings, by the ASCII values, by the sum of the ASCII values, then we will the solution will tell us that yes, these are anagrams, whereas these are not anagrams. All right. So something like this, something like a simple addition, is going to leave us astray. It is not going to give us the right answer. In many cases, it will give us the right answer, but you can always come up with edge cases. Right? So the correct way over here would be to count the frequency of each character, because that does not lose any information. Right? That saves all the information. Is there any other way? So yes, this is definitely a way. A simpler approach could be just to sort the strings. Sort the strings individually. Right? So for example, if I have the string God and if I have the string dog, if I sort God, then what string will I get? I will get DGO. Similarly, if I sort dog, I will get DGO. And the sorting strings, they have to match character by character. Do you agree? If I have two strings, and if I sort both of them, then the sorted value should be the same for the strings to be anagrams. Perfect. All right. So what we can do is we can compare the string A0 with each of the other strings and check if it is anagram. If it is anagram, we will put it in the same group. But we are still comparing every string. We are still comparing A of 0 with all the other strings, right? Simply we are comparing A of A1 with all the different strings. So the time complexity of this is perhaps not that great. What will be the time complexity of this brute force solution? What will be the time complexity of this brute force solution? It will be pretty high, right? So we have to compare every string with every other string. So that is order of n square already. And we also have to check the anagrams, right? Suppose that we are using sorting to check if they are anagrams. So that will be an additional, let us say, not n, let us say k log k. Log k, where k is the length of the string. K is the length of the string. So no. So Shiv Kumar says that we can rewrite this as nq. That is not correct, right? Because we cannot say that this is this is approximately nq, because the length of the string is n, is k. Right? The length of the array, that is n. The maximum length of the string, that is k. The length of the array, that is n. Now this has not been given to us in the question. But we simply cannot assume that each string is going to be the same length as the size of the array. Right? That is not correct. You have to keep these variables separate. Right? Perfect. So that was one approach. Now once again, we can do better. Right? We can do better by using hash maps. So how should we hash the values? What should the hash function be? Suppose that I have this string s, then what should the hash of s look like? What hash function would I like to come up with? So that automatically, if I do hash by chaining, then automatically I get my answer. Yes, so Animesh has the right idea over here. Animesh says that let us store the sorted string in the hash map. So basically, given a string s, the hash of s will be the sorted representation of s. Sorted representation of s. So now things become very simple, right? So if I have, let's say, cat, dog, god, act, and fan, what I can do is I can look at the first string. And if I sort this, I will get ACT. Right? For ACT, I will store the string. I will store the value 1. Right? So this is index 1, 2, 3, 4, 5. Right? And suppose that these are the indexes are starting by 1. Right? So for act, I will store that this string is sorts to act. Next, I will move on to dog. So what is the sorted value of dog? That is DGO. So for DGO, I will store 2. Then I will come to god. The sorted value of god is also DGO. So for DGO, I will also store 3. Okay, then I'll come to act. So the sorted value of act is just act. So I will also store 4 over here. Right? I will also store 4 over here. Finally, I will come to fan. The sorted value of fan is AFN. So for AFN, I will store 5. Right? And that will give us our correct answer. Do you guys agree? This is the final answer. Yes. So what we can do is we can sort each string and store it in a hash map, in a chain hash map. So this hash map stores. This hash map stores a string. So this is the key. The key is a string, and the corresponding value is a list of indices. Right? List of integers. Is that clear? Swapnil is saying, what if we take a map of size 26? It could be done in constant space. Well, Swapnil, you are assuming over here, that the underlying character set is of 26 characters. Right? That might not be the case. It might be the case that the underlying character set has all the Unicode characters. Right? It could be Chinese, it could be Kanji, it could be Devanagari, all these different characters, right? Perfect. So, Prakash over here says, instead of storing string directly, we can convert each character of each string into a range 0 to 25 as frequency. Yes, so Prakash over here says that instead of sorting the string, we can do an optimization there as well. So sorting a string of size k will take us order of k log k time. This will take us order of k log k time, but we can do better. Right? So if we will come to that. So if we look at the complexity of this thing right now, the complexity is how much? We have to go over each string, right, and hash it. How do we hash it? We sort the string, k log k. Right? So this is the current complexity. Now, Swapnil over here, not Swapnil, okay, Prakash over here says that we can also optimize this k log k part. Right? Instead of sorting, we can keep the frequencies itself. We can keep the frequency of character. Right? That is one other way of checking for anagrams. Right? The frequencies should match up. So in that case, our complexity will be reduced to an expected order of n times k time. Right? And then what will our hash map look like? So our hash map will have to store what? So the key will be the frequency array. The frequency array of characters. So the key will itself be a hash map, basically. The key will itself be a hash map, or basically a frozen map. Right? The key itself will be a hash map of frequencies, right? Character frequencies, and the corresponding value will once again be a list of indices. It will be a list of indices, right? Now, when you actually try to code this up, things might get a little difficult because using a hash map itself as a key can become tricky. Right? If you knew that okay, you had the character set of 26 characters only, then instead of storing the hash map of frequency, you could have just stored an array of 26 different values. You could have stored an array of just 26 different values, but you don't know what the underlying character set is. Right? So you will have to store a hash map, and hash maps are not usually hashable. So it is difficult to use hash map as keys. All right? Perfect. Vignesh is asking, why are we seeing Rabin karp method over here? Well, Vignesh, Rabin karp method for string matching is just another very simple. I mean, it's not that difficult. It is just another hashing technique. And that is the next thing that we are going to come to. All right? Perfect. Animesh says, what happens if the number of characters in a particular string is more than k log k? Well, Animesh, that is not possible. Right? So over here, k is the length of the largest string, of the longest string. Right? So if k is the length of the string, then it is not possible for the number of characters, in this string to be greater than k. Right? The number of characters has to be less than or equal to k. Is that clear? Yes? Yes. So Deepanshu over here is saying that if we go with this particular approach, if we go with this array approach, then the space complexity will be high. Exactly, Deepanshu. So suppose that our strings are Unicode strings. Suppose our strings are Unicode strings. So how many different characters does Unicode have? Does anyone remember? How many different characters does Unicode have? Unicode has how many characters? It can support up to 65536 characters. Right? The number of characters in Unicode is huge. Right? So if we were to go with this array approach, if we were to store this array approach, then we will have to store an array of size 65536 for every string. That is very difficult. No, guys. ASCII has 256 characters. Unicode is much larger. Right? ASCII only has some English character, some English letters, some mathematical symbols, some accented letters, right, and some box drawing characters. But Unicode has a lot many letters. Okay, so this is not going to work, which is why we said that let us not keep an array. Let us not keep an array. Instead, let us keep a hash map of the frequencies. But once again, if we are trying to keep the hash map, then things will get tricky because hash maps are generally not usable as keys. Right? Vignesh is asking a very good question over here. Vignesh says, sir, I have a doubt. When we are doing competitive coding online, will the online judge also check the space complexity of our solution? And yes, Vignesh, that is true. I mean, when you go to interview bit, when you go to Scalar Academy and interview bit, our online judge also checks the space complexity. Right? So we make sure that the memory that your particular program is using, the memory that is being used, we just monitor the memory that is being used. Right? And this memory has to be within a reasonable limit depending on the programming language. All right? Perfect. So let us move on. I hope this solution is clear to everyone. All right. So the most optimized approach for this will be order of n times k. Right? If we do the hash map approach, so hash map of hash maps, hash map of hash maps, it is not that simple. But otherwise, we can at least do it in order of n times k log k. Right? If we store a hash map of sorted strings. Sorted strings. All right. I hope that is clear. All right, now let us move on to the Rabin karp algorithm. So far, in both the questions that we have seen, we were trying to come up with our own hash function. We were trying to come up with our own hash function so that we could simplify our life. Right? We could simplify our life. Now, Rabin karp algorithm is another such algorithm. It is basically used for string searching. String searching. So let us quickly define what the string searching problem is. Right? So the string searches problem is very simple. You have been given a large string S. Right? This string could be, let us say, a book, right? Or this string could be Wikipedia, the entire text of Wikipedia, right? Or this string could be the entirety of internet, perhaps. Or this string could be all the products on Amazon. Right? It could be any such thing. And you have been given a pattern. Let us say the pattern looks something like abracadabra. Right? And you want to figure out, first of all, whether this pattern exists in my string. Right? That is one of the most important things that we do while we are searching. But more importantly, I need to find where exactly. So suppose that I have this string over here, I have a large string over here, and suppose my given pattern appears over here, then I should be returning the starting indices of all these different occurrences. All right? That is what the string search problem means. Given a large string and a small search pattern, search for that pattern in the entire string and report all the occurrences of that string. We have to report all the occurrences of the string, not just one occurrence. Perfect. So, what is the normal way? What is the usual, most trivial way that you can solve this particular problem? Suppose that I have a string S of size n and I have a pattern P of size m. Then how should I particularly go about searching for this pattern in the string? I can use some sort of a sliding window. Right? So if I have this string, I can first check this particular thing for the pattern match. Then I can shift by one character and then check this particular string for the pattern match. Then once again, I can shift one character and search this string for the pattern match, and so on and so forth. Right? So I can keep a window of p size and I can slide it one character each. I can slide it right one character each. So how much time will this take? Well, let us look at the first window. Right? So we are currently matching this particular portion of size p. So we will have to verify each of these characters, right? That this matches this, this matches this, this matches this, and so on till the end of this. So each checks will take us order of p time. And how many checks do we have to perform? We have to start from this index 0 and we can go up till the index n minus p minus 1. Right? Because this last character will be at location n minus 1. So this is the last occurrence where the pattern P could occur. Yes. So it will be P times n minus P minus 1, which is simply order of n times P. Do you guys agree? Yes. No, now this NP is not that P versus NP thing. Right? This NP is not that. This NP is just the string length of the strings. Okay. Perfect. Now the question is, can we do better? Can we do better? So there are many string searching algorithms. Today we are going to discuss Rabin karp, but in the coming classes we will discuss more complex string searching algorithms. Right? So you can search string using tries, you can search string using automatas, you can search string using n different ways, and we will be covering most of them in the coming classes. Right? But today we are going to talk about the Rabin karp algorithm. Right? Cool. So the Rabin karp algorithm has one special insight. Right? The Rabin karp algorithm says that, all right, let us suppose that you have this particular string. Let us suppose that you have this particular string and you are matching for this particular pattern P over here. Right? You will spend some time, you will spend P time to check if this is a match or not. Yes or no? You will spend P time to check if this is a match or not. Now, when you move this to one right, when you move this to one right, now once again you will spend P time to check if it is a match or not. Yes or no? That is what is going to happen. So can we improve this? Can we somehow reduce this time complexity? So what Rabin and Karp said was that, all right, instead of comparing the strings, let me instead compare the hashes. Let me instead hash the strings. Right? Let me hash the strings and let me compare the hashes. Right? So suppose that we have this particular part of the string, right? And we have this string that we are looking for P. So if let me call this string S dash, right? Let me call this substring S dash. So if the hash of S dash is not equal to the hash of P, right? If I have this hash of P, and if I looked at the hash of this, S dash, right? If I looked at the hash of this S dash, and the hashes do not match, then what can I say? Can this be equal to P? Can this substring match the same? Can this substring be the same as the pattern? No, it cannot be. Because if it is same as a pattern, then the hashes will have to match. Right? If it is the same as a pattern, the hashes will have to match. So if the hashes do not match, then we are guaranteed that not a match. Not a match. But if the hashes are equal, then what can we say? Can we say that yes, they are a match? Can we say that yes, they are a match? Well, not really. Right? That depends on the hash function. Depends on hash function. So basically, if the hash function is lossy, or just give me a second. Yes. If the hash function is lossy, or basically if the hash can have collisions, then a match hash means a match may be possible, right? A match might exist. Right? It is not necessary for the match to exist because it could just be a simple hash collision. On the other hand, if the hash function is lossless, or that is, it is guaranteed to have zero collisions, right? Then yes, a match is same as a match necessarily exists. Is that clear? So depending on our hash function, we know that yes, if there is a match, if the hash functions match, then an actual match might exist or might not exist. But we are at least sure that no matter what the hash function is, if the hashes do not match, then it is guaranteed that the substrings do not match. Yes. All right. So what can we do over here is, once we are trying to compare this particular substring for the pattern P, right? If we choose a hash function that has a certain property, so there's something called rolling hash functions. Have you heard of this? Rolling hash functions. There's a certain property of a rolling hash function. The property is that once you have computed a hash of this thing, if you have to shift it by one character, then you can easily do it. You can easily calculate the hash of this thing in order of one time. Does that make sense? If you have the hash of p, the hash of, let's say, the index I all the way to I plus p, right? Then to compute the hash of I plus 1 all the way to I plus p plus 1, right? You can do this in just order of one time. You can do this in order of one time, provided you have this previous hash, right? Provided you have this previous hash. So Soumya, we will come to an example in a second. Right? We will come to an example in a second. Animesh, we will come to an example in a second. All right, but is this idea clear? That if we use a rolling hash function, then we can perhaps optimize our time complexity. Now let us have a quick look at one example of a rolling hash function. Right? So this is not the hash function used in Rabin karp. This is not the hash function used in Rabin karp, right? Hash function. But this is one just example of a rolling hash function. Suppose that we simply add the ASCII values of the characters. Right? First of all, as we saw that this particular hash function can have collisions. Right? So this is not a perfect hash function. Yes, we just saw that what sort of collisions can happen. Suppose I have the string A and D and I have the string B and C, then the hash of AD will be equal to the hash of BC. If my hash is just the sum of ASCII values, because this will be what? This will be 65 plus 16 or 68, and this will be 66 plus 67. Right? Both will have the same value. Right? However, this is a rolling hash function. So suppose that I have this string. Let me call this A, B, C, D, E, F, G. Right? I have the sum of these. Right? So I have 65 plus 66 plus 67 all the way till some value. Right? Let us say 72. Okay. Now if I have the hash of this. So if I want to calculate the hash of this, perhaps some character over here. If I have to calculate the hash of this, then what should I do? Should I start once again from B? Should I start adding once again from B? I need not. I need not do that, right? Suppose this value was S. Suppose this value was S. Now I can just do S plus the code of alpha minus the code of A. See, right? I can just do this previous sum. I can add the code for this and I can subtract the code for this. And I can very simply calculate the hash function of this entire chunk. Yes, how much time will that take? That will take order of one time only. Is that clear, guys? Yes, Soumya, Animesh, is that clear? An example of a rolling hash function. A rolling hash function is a function such that in which it is very simple to calculate the hash of the next substring once you have the hash of some substring. Right? On my end, the chat has kind of paused. So I am not sure if you guys are not connecting or if my stream has been blocked. So let me just quickly verify my stream is up and running. Just give me a second, guys. I just open YouTube and check that yes, I am online. Hash of the next substring once we have the hash of some substring. Yes, so I think I am online. All right, let us continue. Yes, so Vignesh, yes, this is similar to sliding window sum. Right? This particular thing is similar to sliding window sum. However, this is not the hash function that Rabin karp will use. Right? This is not the hash function that Rabin karp will use. This is just an example of a rolling hash function. Right? Cool. So we will come to the decision of which hash function to use later on. We will come to the decision of which hash function to use later on. Let us first see that once we have this, what will be the time complexity of our total overall algorithm? Right? What will be the time complexity? So I have this large string S of size n, right? And I have some pattern P of size n. So what I am doing is I am hashing. So first of all, I will calculate hash of P. I will calculate hash of P. How much time will that take? That will take me order of m time. Yes, because I have to calculate the hash of P. That will require going through each of the characters. Now I will start matching from here to here. Right? I will start matching from here to here. I will calculate the hash of this thing. I will calculate the hash of this thing and I will check if the hashes match or not. If the hashes do not match, if hash does not match, then what will I do? I will slide right. I will slide my window to the right. And how will I slide my window to the right? To calculate the hash again, I will remove the value of this thing. I will remove the value of this thing and I will add the value of this thing. right? And that will allow me to recompute the hash of this particular substring. Yes. So recomputing the hash will take me order of 1 time. So sliding right will take me just order of 1 time, right? If the hashes do not match. But if the hashes match, if hashes, basically else, if the hashes match, just give me a second, else, now what can I say? If the hashes match, as we just saw, that depending on the hash function, it is not guaranteed that the pattern exists, right? Because it could just have been a collision. It could just have been a spurious match. In that case, what do I do? In that case, I have to verify if my match is correct or not. Right? So else verify. Else verify. How do I verify? Verification is very simple, right? I look at the first character, I look at the first character, second character, second character. I check if all these characters match. Right? Suppose my hash was same. Just to confirm that the string is actually the same, I can compare it letter by letter. So verification takes me order of n time. M time, where m is the length of my pattern. Yes or no? Perfect. And so this is part of the inner loop. This is part of the inner loop. This is code of the loop. And how many times are we repeating this? We are doing this for every window. Right? We are doing this for every window. And how many windows are there? There are order of n windows. Right? There are order of n windows. So basically what will happen is our time complexity will look something like this. If our hash function, if hashes do not match, if hashes do not match usually, or basically if there are less collisions, if there are no collisions, just give me a second guys. There's something wrong with my tablet today. All right. So basically, if there are no collisions, then what will happen? If there are no collisions, then every match is a guaranteed match. Right? Every particular match is guaranteed to be correct. Right? On the other hand, if there are collisions, if there are a lot of collisions, then every match, most of the matches will be spurious. Right? Most of the matches will be spurious. So can someone tell me what will be the worst case and best cases of this algorithm? So if there are no collisions, what will be the time complexity? If there are no collisions, then what will be the time complexity? Well, the time complexity will just be order of n. Right? The time complexity will just be order of n plus m, because if there are no collisions, then I'm guaranteed that as soon as the hash functions match, I'm guaranteed that the pattern exists. I don't have to verify it. Do you guys agree? If the collision possibility was not there, then this verification step is unnecessary. I don't really have to do that, because every hash function match is guaranteed to be a pattern match. Right? But if there is a chance of collision, then I have to do verification again and again and again. Right? I have to keep doing verification. So in the worst case, as we see from this loop, this loop can go order of n times order of m. Right? So the total time complexity over here can be order of n times m. Right? And this time complexity, as we see, this is no better. This is no better than the brute force. If we look at the previous brute force solution, just give me a second. If we look at the brute force solution, then the brute force solution was just order of m times n. Where did that go? N times p, right? So it is no better. Rabin karp is no better if the hash function has a lot of collisions. Is that clear? So the entire functionality of Rabin karp, the practical performance of Rabin karp, will be based on whether you choose a good hash function for your use case or not. All right. So Rabin karp basically, best case with perfect hash. This will take us order of n plus m time. Right? But in the worst case with imperfect hash will take us order of n times m time. Right? Now the question arises, what hash function should we use? All right? So can someone come up with a nice idea of a hash function? Can someone come up with a nice idea for a hash function? Well, we would want the hash function to be as lossless as possible. We want to retain as much information about the string as possible. For example, if we have the string ABCD, if we add the ASCII values, are we retaining a lot of information? We are not necessarily retaining a lot of information, right? Because the hash of this is the same as the hash of DCBA. Right? So we are not retaining a lot of information. So this is a very lossy. This is a very lossy hash function. What will be the perfect hash function? What will be the completely lossless hash function? Well, I can encode each string into an integer. Right? I can actually encode each string into an integer, right? Because every string, when we look at it, every string is just stored as bits and bytes in the memory. Right? Everything in the computer is just zeros and ones. So I already know some way of encoding a string into an integer. Right? But if we are not sure how to encode the string into an integer, I can manually do it. Right? Suppose that my character set was ASCII. ASCII can have 256 different values. Right? ASCII can have 256 different values. So I can just treat this as a number in base 256. Right? I can just treat this as a number in base 256 and convert that number into base 10. Do you guys agree? So what is this number equal to? What is this number equal to? So what is D? D is 97 plus 4. Right? That is D. So this is 101. The ASCII code of small d is 101 times 256 to the power 0. Plus what is C? It is 100 times 256 to the power 1. Plus B is 99 times 250. Okay, I guess I messed up. This is 100. This is 99. Right? This is 98 times 256 to the power 2 plus 97 times 256 to the power 3. Yes or no? This is how I can make sure that I have the entire information of the string. If I have this hash function, then it is guaranteed that there are no collisions. Right? Because I'm not losing any information. I'm just encoding that string. I can go from here to here and I can go back. Right? So there's no loss of information. But would this hash function usually work? Is it really possible to have a hash function like this? Is it possible practically to use a hash function like this? Not really, because these hashes can get arbitrarily large. Right? Suppose that my pattern is of size 50. Right? My pattern has size 50. Right? So in my pattern, this character, the ASCII value of this character will be multiplied by 256 to the power 50. That is ridiculous, right? That is a huge number. So I cannot possibly store this in a 64-bit integer or even a 128-bit integer. Right? That is not possible. So I have to reduce the size of the hash. Right? I have to reduce the size of the hash. And one common way of doing that is to just take a mod. Right? Mod or modules. Yes. What should we usually take a mod by? What should we try to take a modulus by? Well, we can try to take a modulus by the size of our hash. Right? Suppose our hash, we can store 64-bit integers as hash. Then we can simply mod it by 2 to the power 64 minus 1. All right, we can simply mod it by 2 to the power 64 minus 1. All right. Usually, it is still a better idea to use a large prime number for modding, right? Because if you use a prime number, it has a slightly better distribution for the hashes. All right. Perfect. So Rabin karp says this. Rabin karp just says this, that given a particular string, if you are trying to find a pattern, first of all, find the hash of the pattern. Right? And this is the hash. Hash is just the encoding of the pattern. Hash is just the binary encoding of this pattern, right? With some modulus. N. Right? With some large prime number P. Is that clear? Once you have calculated this hash, then compare the hash of each substring. Compare the hash of each substring with this hash. If it is not a match, then simply slide the window to the right. If it is a match, then please go and verify. Right? Please go and verify. Now, is this particular hash function rolling hash function? Is this a rolling hash function? Suppose that you have the hash value of this, right? So you have A, B, C, D, right? And let us say that the character set is suppose 256. Right? So this is 256 to the power 0, D times plus. So let me just read this. This is just D times 256 to the power 0, right, plus C times 256 to the power 1 plus B times 256 to the power 2 plus A times 256 to the power 3, right, where A equals to 97, B equals to 98, C equals to 99, and D equals to 100. So this will be my actual encoding, and I will also mod this with some value. I will also mod this with some value. Let us say M. Okay, this is the Rabin karp hash function. Is this a rolling hash function? Is this a rolling hash function? Basically, if I add a new character over here, E, suppose 101, then can I calculate the hash of this part? Can I efficiently calculate the part of hash of this part? Yes, no? Well, yes, I can. Yes, I can. Let us quickly see how. So what is the hash of this part? Right? Let us see. Let us first write what the hash of this part is. The hash of this part is this. B times 256 to the power 3 plus C times 256 to the power 2 plus D times 256 to the power 1 plus E times 256 to the power 0. Do you agree? This is the hash of this BCDE. Do you guys agree? All right. Let us see if we can convert this. If we can take, if we can somehow get this value from this value. All right. So first of all, what we will need to do is we will need to subtract the value of this. So let me just put some space in over here. So what we can do is, first of all, from this we can subtract A times 256 to the power 3. Yes. Now whatever remains. So what part will remain? This part will remain. Right? This part will remain. But we see that this part has one less part. Right? So currently B is being multiplied by 256 square. We need B as 256 to the power 3. Similarly, D has been multiplied by 256 to the power 0. But we need D multiplied by 256 to the power 1. So we just multiply the remaining thing. With the base 256. Right? And then we just add this last value. Then we just add this E times 256 to the power 0. That is going to give us the new hash function. Yes or no, guys? Right? This is the same as binary. Right? If you have this binary number, and you know the base 10 representation of it, or if you have the base 10 representation of it, then you can remove this and add something over here, right, to get a new particular value. That is perfectly valid. You can totally do that, right? So this is what the Rabin karp hash function is, Rabin karp hash function. And yes, this is a rolling hash function. Right? Now there's one catch that you have to understand over here, that because this is a modulus, this is going to work, right? Basically, do you guys know that modulus distributes over addition equals to A mod M plus B mod M? Right? So notice that there is some loss of information happening over here. Right? Once you have calculated this, after that you are losing some information because of this mod. Right? But that doesn't really matter, because modulus distributes over addition. It also distributes over subtraction. So notice that we have to subtract this value, but we can do that because we are using mod. Similarly, we have to multiply this value, and modulus also distributes over multiplication. The only reason we can do this is because we are using the modulus operator. We are losing information in a manner that mathematically makes sense. If we had lost information in some other manner, we would not have been able to reconstruct it. Right? We would not have been able to have the rolling hash property. Is that clear? Perfect. So this is basically it. This is the Rabin karp algorithm. And once again, you will find the assignment. You will find a set of problems on the Rabin karp hash function in the problem description. Right. So in the problem description, there's a link to an assignment. Just go over there so that you can actually practice coding this. Right. So we discussed the approach, we discussed the intuition, but unless you actually sit down, code it out in your programming language, debug it, make sure that it works for all the different test cases, make sure that you have removed all the edge cases, and you take care of the boundary conditions. Only then will you actually be able to learn this stuff. Right. So please check out the link and practice it. All right. So this was just some string matching using the hashes. Going forward, so in the next class, we will be covering a lot more other string matching algorithms. So we will be covering things like the KMP, we will be covering things like the Z algorithm and other string matching algorithms as well. All right. Perfect. Then let us end today's class. And let us see you guys tomorrow. So once again, for those of you who were new to the stream, we are having these classes every day from 6:30 p.m. to 7:30 p.m. All right. So every day at the same time on Scalar YouTube channel, we have these live classes. Can we have a session on sliding window? Well, AG is asking that, can we have a session on sliding window? Well, AG, we can certainly plan for that. Right? So if there is sufficient demand for it, we can certainly have that. Okay. Perfect. Also, apart from the assignment link, there will be also a link to the chat, right? In the problem in the video description. So over there, if you go over there, you will be able to chat, or if you will be able to join our chat, and you will be able to talk to your peers. So all the people who are watching the YouTube live, all the students at Scalar, the mentors, the teachers at Scalar, so that if you have any question, be it regarding this particular lecture, or be it regarding anything else in your programming curriculum or in your programming career, then you can ask us for help, and as and when we have time, we will be able to help you guys. All right? Perfect. Surit says, are we not going to do a modulus on the next window? Yes, Surit, we are going to take a modulus on the next window as well. Right? So after we have done this, so basically, so we have the hash. We have the hash of previous window. Right? Let me call this h. So what we are essentially doing is we are saying h minus what was the first character, right? Character 0 times base to the power the length of p. Right? Base to the power length of p. So we will subtract this. Then we will multiply the result with the base. Right? Then we will add what? We will add the new character. Character, let's say, call this new. And let's call this character old. We'll add the new character, and then we will once again take the mod with the same value m. All right. Perfect. So Arpit and Animesh, the next class is going to be on string matching. Right. So today we were looking at string matching from a hashing point of view, right? From the Rabin karp point of view. Going forward, we will be looking at string matching with other algorithms. So the Z algorithm, there's the KMP algorithm, which use some sort of automata. You can also do string matching using tries. So we will be covering all those different topics. Right? Perfect. Length minus 1. Yes, my bad. Length minus 1. Thank you for that, Rajiv. All right, let us end the lecture in that case. See you tomorrow, guys. Have a nice day. Bye-bye. Varun over here, just let me end with this. Varun says that computing this will take a lot of time, right? So if, let us say, if my pattern is of length 50, then how will I really calculate base to the power 50, right? Base to the power 49, some value times base to the power 49. That will be really difficult, right? Well, not really. As we saw that mod distributes over multiplication. There is something called an exponential mod, right? Binary exponentiation. There is something called binary exponentiation with mod that can compute a to the power p mod m in log of p time. All right, so it can also be done very, very fast. So don't really worry about that. Okay. So thank you guys. Let us end the lecture. See you in the next class, same time tomorrow. Bye-bye.